Good afternoon, everyone. Welcome to lecture 3 of the course by Professor Bucher. And before I ask Professor Bucher to start sharing his screen and start with his lecture, I just wanted to alert you that next week we will have a slight change in program because unfortunately Professor Bucher will be traveling next Tuesday, and he offered us the possibility to have the last lecture of the course either on Wednesday or on Friday. Yeah? And what we decided we will do, I will open up just now a poll, and you can choose your preference, and then we will share an announcement with the new day and time for the last lecture of the course. Yeah, I hope that is okay for everybody. Yeah, Martin, please. You are most welcome to share your screen and start your third lecture of the course.
I have to unmute myself. Okay, so we're going to continue with our discussion of the microwave background. And during the last lecture, we talked quite a bit about theory. And I sort of wanted to show you more graphically what you can learn from the microwave background. Let's see, how does this? Okay, so these are some animations of the CNB Power Spectrum, which we'd already seen for a certain choice of parameters. And you'll see animations that sweep through different values of the parameters so that you can see what changes. So let's see, let's hope this works. Yeah, so this is from Wayne Hu at the University of Chicago. And you see, this is the multipole number on a logarithmic scale. And let's see, I'll move. And here is the plateau at large angular scales. And then you see these acoustic oscillations, and then they dampen off due to what is known as self-damping or viscosity, basically. And there are many parameters that can be varied, but here we have the baryon fraction, so compared to the critical density, and it's convenient to factor out the Hubble constant to remove some degeneracies. So you see that the first peak, the height of the first peak, is a very sensitive probe of the amount of baryons. Although if you would just look at this in isolation, you wouldn't know, well, maybe you could vary some other parameters and sort of find another way to get the same thing. But we can only do animations in one parameter at a time. So these are, let's see. Then here we're looking at the curvature of the universe. So omega k is the sort of missing matter. So if you look at h squared is 8 pi g over 3 rho, then there is a minus k squared over a squared. So if you don't have enough matter to close the universe, then formally these low density universes, you just make all the omegas add up to 1. And this is a geometrical effect because the universe becomes hyperbolic. So that means that if you have in flat Euclidean space two, lines of sight a certain angle apart, they just spread like a triangle. So the distance is on a surface is proportional to, well, it's equal to the angle times the distance. But then in a hyperbolic geometry, there's a sort of exponential divergence. So it's sort of like a diverging lens. And these spots, which sort of correspond to the Doppler peak in real space or angular space, they get smaller. And you have a prediction that if the universe is negatively curved or to any significant degree, then this first Doppler peak, which serves as sort of a standard ruler, will be at smaller angular scales. So, and there's also some stuff that happens in the extreme cases at low L, which we could talk about. So this would be, if we didn't have a cosmological constant, we would sort of be down here. And you can see this is a very spectacular effect. So it's good to sort of think about these different effects and qualitatively try to understand what the effect on the power spectrum is. Let's see, this is another combination of parameters. Here, one has the amount of dark matter. So if you have 6 or 7 parameters, then you need to use mathematical methods to fit the parameters. But this is just a visualization that's useful. Let's see. Here you also have the polarization, and we'll talk about that a little later. Okay, the next topic that I wanted to talk about is CNB polarization. So this is much harder to measure and wasn't one of the first things to be discovered, that the CNB anisotropies are polarized. And you should think of the polarization as sort of a bunch of lines on the celestial sphere, so you can sort of think of, you take a linear polarizer and you can't really distinguish between the intensity, if you have one orientation and then you have it a half turn. So it's sort of like a double-headed vector, or you can represent it as symmetric traceless tensor on the celestial sphere, but it's a spin-2 object. So this is a representation of the polarization, and there are other representations, and we'll see from the theory why this is a very interesting thing to look at. So let me return to this picture and where we derived this Sax12 formula. And one of the assumptions was that there is a sort of, in this approximation, an instantaneous transition from the universe being completely opaque to completely transparent. And as we said, that this is not exactly what happens. But if this were what happened, then you wouldn't see any CNB polarization. However, the scattering of electrons, of photons off of electrons is highly anisotropic. And if you have scattering at right angles, then there's one polarization that it just can't scatter just from the fact that there's no longitudinal polarization of the electromagnetic field, or that it doesn't propagate. So heuristic way to think about what you're looking at is when you look at the polarization at a certain part of the sky, you're seeing the CNB anisotropy as seen by the electron of last scatter. And then that gets multiplied by the distance between last scatter and next to last scatter. So if that distance is very large, that is, if this transition from opaqueness to transparency is very gradual, then you get a second derivative times that distance squared. So this is a very sensitive probe of the distance, the thickness of the surface of less scatter. Of course, for making precise predictions, you have to go beyond this, and the Boltzmann equations, or linearized Boltzmann equations that I showed you, have to be integrated, and there are codes like class and chem that do that rather mindlessly. And that doesn't give you very much intuition about what's going on, but it'll give you more accurate answers. There's another sort of decomposition that shows you why looking at gravitational waves, if you want to see gravitational waves from inflation, you want to look at the CNB polarization. I realize now that there's a del squared missing here. So let me explain the difference between E modes and B modes. So you will hear that the B modes are the telltale sign of gravitational waves from inflation, and I will explain to you why. Okay, so here I put the spherical harmonics, and I'm generating a field, tensor field, traceless symmetric tensor field on the celestial sphere to represent the polarization with these rotational quantum numbers. So this operator, and there should be a del squared here, is spin zero. I mean, you don't need to specify any direction. If I change the basis on the celestial sphere, I get exactly the same thing. Now we could just have any function here, and we could take a superposition, and we just get an E mode. And then here you have two derivatives, but you have the completely anti-symmetric tensor on the celestial sphere. And you can work it out that this is rotation by 45 degrees. Now, this is a pattern, a polarization pattern like this that can be represented by a potential. And then this is one that can't. I mean, this 45 degree rotation will be different in different rest frames. But if you have a linear theory, like inflation with a scalar field, you can only excite the E mode, but you can't excite the B mode. So if we had a huge amount of gravity waves from inflation, then we could go to the, pattern of temperature anisotropies and the pattern of E mode anisotropies, and the shape would be different. But with the B modes, you have a lot more sensitivity because this just shouldn't be there at all because of symmetry reasons. Now there are foregrounds that sort of mess things up, and those have to be subtracted successfully. So it's not quite as easy as it sounds, but this is this slide really explains to you why there's so much excitement about looking for B modes. And as we said last time, quantum mechanics says that all fields in an expanding universe are excited. So the same thing would be true for gravity waves. And it turns out you're probing what is the expansion rate during inflation when the scales that you're looking at, the angular scales, leave the horizon. So this is a plot of all of the anisotropies of the microwave background, including the B modes, and the contributions from the scalar degrees of freedom. So the inflaton field are in green, and you can see this is about 1,000 microkelvin squared. So that would be the amplitude on large angles. So you take 1,000 and you get about 33 microkelvin, and that is sort of roughly the scale of the map that you have for the temperature anisotropies. Then the TE are cross correlation. So you see this on a logarithmic scale, this is the absolute value. So this there's a sign change here. So that's why this has this shape. And these are the E mode anisotropies. And this has all been mapped out. So I'll show you a little about experiments. And then for the tensor modes, there's this tensor to scalar ratio. So we don't really know the scale of inflation. This moves this prediction up and down, and a tenth has already been ruled out. And you can see, well, you would add this in quadrature. So if it had been that large, you would be able to detect it from just the shape of the TT power spectrum. This sort of template plus the 6 parameters wouldn't work. But it turns out that the E mode, which hasn't been measured, and the cross correlation and all of that, that it fits pretty well without tensors. But then you can go way down in sensitivity with the B mode because it just shouldn't be there. So you don't have to worry about any of this shape stuff. And there's one background that one can't get rid of, and that is the lensing of the CNB. So that is nonlinear effect, and you get a nearly scale invariant spectrum with a turnoff. It has this shape because it's the lenses are small. So if you look at the lenses on large scales, then it sort of looks like boson noise. On the other hand, this has a simple form, so you can subtract these away. Okay, so this is the theory that explains why the B modes are so exciting, and this would be a very important new test of an inflation, or a prediction that no one otherwise would have made. Okay, let's turn a little to observations. And there's sort of been an alternating experiments from the ground and experiments from space. And they have, different pros and cons. But this is a picture of the Kobe satellite, which in 1992 made the first detection of the microwave background anisotropy. So we already looked at the maps and the power spectrum a little. But here you have basically some sort of a crude telescope that is looking in the sky, or in this case, they're just these feed horns. And I'll explain to you, there are a lot of tricks on how to make this very sensitive measurement. And it's important to appreciate what they are. So this was a satellite that would go around the Earth every 90 minutes, pointing away from the Earth, and also spinning around. And then you had these horns that were looking at the sky and measuring differences. And so you you have a lot of shields to keep away the sun, and you have to worry about diffraction across these shields. And this is just conventional. There are solar panels to provide the power needed, and then an antenna to beam the information back down to Earth. And this is a close-up of the instrument that measures these differences. So you have two antennas, and then you have something that switches very rapidly between them. So why, you really cannot make an absolute measurement to this accuracy to 1 part in 10 to the minus 5. The amplifiers are very unstable, so they're 0 point sort of drifts, and you really have no idea of what it is. It has a so-called 1/f F noise spectrum, which formally would mean that the 0 point would diverge. So, but if you switch very rapidly between these two antennas and then just take out the part of the signal that is at this frequency, then you can measure the difference between pairs of angles on the sphere, and then you can make a map by computer. So this is a sort of experiment where you really need massive computing, and that's sort of one of the characteristics of modern microwave background experiments and elsewhere in astronomy. So we already saw these are the maps that you would have. So this we don't really measure, since we're just measuring differences, but then so you set the differences equal to 0, but then you get this dipole pattern, and then when the dipole is subtracted away, this is what you get. And maps are constructed at different frequencies, and then the galactic contamination is subtracted by looking at different linear combinations. So let me sort of go through some of these observations historically to indicate why this was an exciting time. So I told you in the last lecture about inflation, which is sort of the Best Buy theory today. But before these observations were made, there were lots of other theories on the market that could fit the observations at that time equally well. And here I show you the sort of animation of visualization of cosmic strings. So these would be much tinier, but you have these very heavy strings that gravitate, and they're sort of sloshing around. They go at a fraction of the speed of light. And when they're moving, they create a sort of discontinuity in the temperature, and that creates a pattern. So this was something that a lot of people worked on at the time, and there in the early 90s, there were conferences with big fights, which is a better theory, but there was no way to arbitrate this conflict because there weren't any observations then that could distinguish between them. So here we capitalizing on this isotropy of the underlying anisotropies, we reduce everything to a power spectrum. And we have an estimator of the power spectrum. So this is sort of the sample variance in terms of the spherical harmonic coefficients. And we'll talk a little about nongaussianity, but if the process is Gaussian, this is all you have to work with. So here with Kobe, all we really had was the normalization. And I mean, you can read certain things into this plot, but nobody knew how it would extend to smaller scale. So we went to about 2000 in these other plots or in the animations that we were seeing. Okay, so this is a sort of semi-random paper, causality, randomness in the microwave background. So here you see two power spectra, and one has these oscillations such as those that you saw in the Wang-Hu plot, and then the other has a very broadened Doppler peak where there are no such oscillations, and that would be for something like cosmic strings where, you know, there isn't a growing mode and a decaying mode that would have decayed away, but modes are being excited at all times. So you got something very broad, but definitely not this, you know, very sharp ringing. So is what we saw in the previous plot, how is it going to continue? So that was the big question in, you know, 96, 98 or so. Then this is a bit of a personal selection, but one of the things that I worked on at that time was a universe without a cosmological constant. So there were all these indications that omega matter was about 0.3. In other words, what you see is what you get. And people didn't like the cosmological constant. And this was possible by having two stages of inflation. And these bubbles, you can see that they're the surface on which the inflaton field is constant. These are hyperboloids that have a sort of an asymptote of a light cone. And then this is sort of the Euclidean bubble nucleation. And the prediction made was that the Doppler peak would be over here rather than here. But you can see this data is not very good, and you know, you can argue, oh, you should believe this point, not that point, and what about the error bars? So there was suspense for a number of years, and then, you know, eventually this model was killed because this is jumping ahead a bit to Wmap, the pre-Planck data, but you can see that all of these oscillations, or the first three, are mapped out very precisely. Well, at least the first two. These are experiments from the ground. So this inflationary model with a cosmological constant fits really well. So that killed the hyperbolic universe theories and the topological defect theories, but they could always claim, oh, well, there could be cosmic strings that are subdominant, or you could have a universe that's slightly hyperbolic. But such proposals, while interesting, sort of are not aesthetically very pleasing. You would just like a simple model that can explain everything. And if you can explain everything with a simple model, then you should just stop there. Okay, so here you can see that this was a balloon experiment called Boomerang. This is a Nature paper, and here they're announcing, that the universe is flat and not hyperbolic as I had wished, and my collaborators and a lot of astronomers. And here you can see the, Boomerang observations, while not perfect, they really map the position of the Doppler peak out with a fairly high degree of precision. So if you go beyond that, then you could ask, well, we don't want to stop here. We want to know, is the observations become more precise? Is this sort of agreement with a simple inflationary model? Is that going to continue to work, or are things sort of going to fall apart? So you want to map to smaller angular scales, and also with higher sensitivity. So here you might see some, discrepancy with the second peak, but it's not really all that clear. Okay, this is some other, there are also these isocurvature perturbations. You could vary the amount of baryons from compared to the number of photons in different places. You can do weird things with neutrinos, and you get these isocurvature modes. And here, you can see that by adding these individual contributions, you can get something that has a lot of isocurvature and creates almost the same temperature anisotropies with no isocurvature modes, but then with the polarization, this all falls apart. So this was an argument to do the polarization. This would be the E mode with high precision. Let's see, I'll talk a bit about Planck. So Planck is a European satellite, I guess principally France and Italy, but there were a lot of other countries, the UK, Spain, Norway, Denmark to some extent, and also the Americans participated. So this is the latest CNB experiment from space. And here you see this in a clean room at Alcatel, which was the industrial contractor that put the satellite together. And you basically have this telescope with these shields to keep out the sun. And there's also a lot of heat that has to be gotten rid of. And then this is the all the electronics, and underneath would be the broadcast back to Earth. And these are the feed horns. So they're quite a bit like the Kobe feed horns, except because of the telescope optics, you get a much finer angular resolution. This also used different technology. It used these cryogenic bolometers, which we can talk about some of the technology in the next lecture, but this is sort of a bit related to how they measure your temperature with this camera at the airport, but it much more sensitive. So this is the focal plane, and sort of like brass instruments, the smaller horns correspond to higher frequencies, and the low frequencies are these horns in the suburbs, you could say. And this is somewhat a version of Wmap, but with improved technology. So these are the Planck sky maps, and they start at 30 gigahertz and then step up and go to 800 gigahertz. Wmaps stop around here. So you couldn't really probe these foregrounds at high frequency. So here you see at 70 gigahertz, the galaxy is sort of most invisible. And then the emission around the galactic plane, which is at the equator in this projection, it widens. And this is synchrotron radiation, which means that in our galaxy, you have two things. You have magnetic fields, and then you have non-thermal equal electrons or cosmic rays that sort of spiral around, and they emit, and the emission gets hotter at low temperatures. So the CNB is a black body. So all of these would have the same pattern if you just had the CNB. And then at higher frequencies, you get interstellar dust. And this is heated by ultraviolet light from stars. And then there's re-emission in the infrared. And here you can see that there's hardly any microwave background. So if you want to do cosmology, what you want to do is find some sort of linear combination, or you can be more clever and have, non-Gaussian ways of removing these foregrounds, but you want to observe at many frequencies in order to just get the pristine CNB. And this is, well, not actually the map that was used to get the power spectra, but this is a linear combination that proves that you can get rid of the galaxy. So you can sort of ask yourself, well, can you see any remnants of the galaxy in this image? And arguably, no. So this image proves that the foreground removal that I talked about in the last transparency, that it can actually be done. So here we see, this is Wmap 2015. There's some more recent 2018 analysis, but it's much the same. And you can see in red, the theory, and you can see how there is this remarkable agreement basically up to the resolution limit. So this goes much farther out than Wmap. And in the next lecture, I will sort of explain to you why Planck was a better instrument. It involved some more risky technology. And here we can look at the residuals. So this is a little like trying to see a pattern in tea leaves, and there's some intriguing things. There's sort of this dip here, and these are sort of overall on the low side. So a lot of papers have been written about that. Here, there's a different scale, but you know, you can try to find patterns. But if this were really wrong, you would sort of see, well, things like this. But here the agreement seems to be pretty good. And sorry, here you see the polarization. This is just the EE, so there's no bipolarization detection. And there's some problems with systematics and leakages, so you can sort of see arguably some patterns here. But the fact that there's a pretty good fit tells you that the polarization and the temperature, that they're telling the same story. And if the theory were completely wrong, that wouldn't be what you would be seeing. These are the cosmological, the model parameters, and most of them are determined to about the percent level. If you look at this, well, you can sort of compare the shifts between different years of the Planck data, but I won't get into that. Okay, cosmological parameters. Well, you see plots like this all the time, and they sort of look the same. They start to look all the same, but here let's see, this is angular diameter distance, I believe. This is the amount of baryons, the amount of cold dark matter, the normalization of the power spectrum, the spectral index, so the power law, the deviation from 1, and the reionization optical depth. And I think the interesting thing to see here is that if you look at the green, which is just polarization, and then you look at the red or the blue, which are the same because most of the precision is coming from the temperature anisotropy. Well, they're telling the same story. If they didn't, you would have a green air ellipsoid, and then you would have the red completely outside it. And then you would, that would really be a clue that the theory is wrong, that polarization is telling another story than the temperature anisotropy. And we can, I won't go into the details of this, but here you see various sort of candidate inflationary models. And this is the slope of the power spectrum. And then this is the tensor to scalar ratio. And as it was constrained by Planck, and you can see that there are models that are ruled out. Phi to the 4 was ruled out by Wmap, or you could talk about shooting into a dead corpse. I think that was the way we described trying to say that this was something that Planck had done. But this connects fundamental physics to the microwave background observations. Okay, I'm sort of running out of time, but this is the Planck. I'll just go through the
Martin, are you still there?
I also could not hear Martin.
Yeah. I don't know, let's wait 30 seconds. Maybe he reconnects, because he's still connected, but okay, maybe to kill the time while Martin returns, let me share the result of the poll. So I hope you can see it. So it looks like the last lecture of Martin we will have on Wednesday, the 29th of September at 4 p.m. Yeah, and I'm sorry for this inconvenience, but Martin is traveling on Tuesday. Yeah, okay. Let's wait a second to see if he maybe reconnects. But we were almost almost reached the end. Let me see what we can do. Okay, let's wait. And here we go. Here he comes. Martin, welcome back. You're muted, Martin. You're on mute.
Okay, and let's see. So I have to share the screen again. Oh, so people prefer Wednesday at 4.
Yes, yes. I try to kill the time with sharing the poll.
Okay, so that's okay, decided.
Now I close it so it doesn't disturb anymore. Yeah.
Okay, so we're okay, this is the lensing power spectrum. And here you have multi-pole number, and then this is the lensing potential. And you can see that this is rather well constrained. There were detections before first in cross correlation, but this is the first relatively accurate determination of the lensing. And this is going to improve a lot in the future. And we can talk about why that's interesting. Then another issue is the Gaussianity. So I gave you some all these formulae where you assume that fluctuations in the microwave background temperature is Gaussian, or very nearly Gaussian. And I told you why, because inflation is well described by almost free field theory. This is what one might expect if inflation is true. But then we can look for non-Gaussianities and we can try to constrain them. And this is this parameter F and L. So this is the pattern of non-Gaussianity that you would expect in certain models. And there were hints that it was around 100 or so. And it turns out to be exceedingly small. So this is something very interesting and also tends to confirm inflation. Okay, I'm going to hear some sort of more futuristic things that you could expect. Search for Doppler peaks and non-Gaussianity. This is hardly observable. Let's maybe, I wanted to talk about searching for B modes, but I think it might be better to start that discussion and those observations in the next lecture, because we don't have much time, and maybe we can take some questions now. So thank you very much for your attention.
Okay, thank you, Martin. And Inge indicated in the chat that he had a question, and I've allowed him to talk. So Inge, you're welcome to ask your question.
Okay. Hello. Yes, am I audible?
Yes, I can hear you at least.
Okay. Okay, great. Yes. Yeah, it's nice to hear Martin to give a historical review on the CNB development, and that's really something very interesting. So actually, I have three brief questions. One is, if we are able to, the first one is about the tensor to scalar ratio. It's about the CNB B-mode power spectrum. So if we are able to completely de-lens the E mode mixing into B mode, and if we are able to completely suppress every foreground we have and only limit the whole thing by cosmic variance, can we have a infinite signal noise measurement on R? If not, then what will be the R limit? I mean the fundamental limit that we can measure.
Well, I think that's a very good question to which nobody really knows the answer. And, there are lots of forecast papers claiming this or that is possible, but till you actually do it, you really don't know how hard it will be to get rid of the foreground. So let me sort of explain the question a little. So when we, well, I guess maybe I can share the screen again, and I'll find the, wait, is this, how do I? Okay, so this is the image, and what Yingxie was referring to is you have this gravitational lensing pattern, and the way I was describing it was that you just treat it with noise. But in theory, the lensing can be detected using, how patterns on very small angular scales are distorted. If you have very high sensitivity and high resolution, and then you can de-lens and basically subtract this, and it ceases to be something that, you've denoised your map, and you can forget about this red foreground. Then there are the other foregrounds, and I just showed the temperature maps, but in polarization, there are similar maps. And since the polarization is, if the foregrounds is larger than the polarization of the microwave background, you'll see the galaxy much wider. So will a simple linear combination produce a map like this or not? And how will one know? Well, there are a lot of forecast papers, but they tend to be best case scenarios, because you could always make up a very complicated model. So people will have to do these experiments, and we'll see how far we get. But there's no reliable way of predicting where there will be sort of unsurmountable obstacles to measuring tensors at a lower level. So I think I refuse to answer your question to some extent, because I don't think everybody knows.
Yes, thank you. Yeah, and my second question is this. The second question is about technologies of measuring the CNB, and I saw there were papers at early time, maybe 20 years ago, in between the late 1990s to the earlier 2000s, talk about using the interferometry as a way of measuring a CNB. But then later on, when Planck and Wmap and Planck, etc., all of this like ACT developed, that technology is not going to be used in the current measurement of CNB. And why is that? Why people gave up interferometry as as one of the major tool to measure the microwave background and therefore radio astronomy generally?
Well, interferometry is very useful at low frequencies, where you if you want to have high resolution and have a big telescope, it's just too expensive. It has to be too big. The argument that was made would be that there are all sorts of systematic errors, and these sort of imager telescopes would be dominated by systematic errors. But that hasn't really been shown to be the case. And so I think most people feel, well, one should just push ahead with imagers, which are, well understood, and we should deal with problems that are known, rather than try some alternative technology that is more complicated and you know, not really tested.
I see.
That's my slightly biased point of view on that.
I see. Okay, thank you. And I'll read the last question, which is quite quick, is you have shown the focal plane or Planck, which, I mean, if you can go to that page. Yes, exactly. So the middle panel, which is really a good position, is for HFI. Whereas these big horns that we can see are which are surrounding this middle panel are the low frequency instrument. And because the position of these low frequency horns are kind of not in the center of the focal plane, would that produce some problems when you calibrate the map? When you get a, when you get the time order data, you need to form a map, right? So you would need to, I mean, with this off center, what I mean that with this off center of the LFI horns produce a problem while you produce a map.
Well, if you design a telescope, and this would be the same for an optical telescope, I mean, you sort of want to make a large focal plane that you get a lot of aberration, and the larger you make the focal plane, and the aberration is more of a problem for the high frequencies, because there's less smearing, so you sort of want the diffraction to be roughly equal to the aberration. So you can use this sort of low quality real estate in the periphery for the low frequency instrument, and you use your best real estate where you really need to have a small amount of aberration because you get a less diffraction. So that's sort of the thinking behind it. So of course it would be better to say build another telescope and put these all in the center, but it's a question of cost and making something that is good enough to do the job. There are also sort of considerations of compactness. This is cooled a lot more than this, so you sort of want them all together.
Yeah, thank you. Yeah.
I mean, engineering is about making something that's good enough, and not choosing everything ideally to do an experiment like this at the best experiment at a given budget.
Yeah, exactly. Yeah.
Okay.
Other questions?
I do not see any other questions, and no attendees are raising their hands to indicate that they might have any questions or written them in Q&A. So I assume that we can, and take into account that it's already 3:10, so we could probably finish for today. And the next lecture will be not next Tuesday, but on Wednesday, yes, 29th September at 4 o'clock.
No, it's not Monday, it's Wednesday, Ilya, it's Wednesday.
Yeah,
Wednesday.
sorry.
The next lecture is on Wednesday, Ilya. 29th September. So tomorrow in a week at 4 p.m. Yeah, that was the outcome of the poll. Yeah. So Martin, thank you so much, and Ilya, thank you so much for moderating the question. And yeah, please, we will send out latest tomorrow a reminder with the new time of the last lecture, and the Zoom link will remain the same. We will just change the time of the last meeting. So Martin, thank you so much again for an excellent lecture. And we are really looking forward to see how the story ends next week. Yeah. And probably on behalf of everybody, thank you very much for visiting us in Durban. Yeah, you were the first visitor that we had in a long, long time. Thank you very much.
Well, thanks for having me.
And safe travels back home. Yeah. Thank you. Thank you very much, everyone. Stay safe. Yeah, and we will see you latest next Wednesday. Yeah. Thank you.